This video is going to show how to do principal components analysis with VisuMap software. We will first start VisuMap, and then import a sample dataset into VisuMap. The data we are going to import is in text format. There are several different ways to import data of such format into VisuMap. The simplest way is just dragging the file icon into VisuMap window. When received such data file, VisuMap will analyze its content and display an option window to give us some control on how to import the data. We see that VisuMap has found out that the data file has a headline, and suggests to use the values in the ID column as identifiers for each data point. Through the first drop-down list we can select any column as data point identifiers. But, in our case we just use the suggested column. Now we have imported the data into VisuMap as a new dataset that is internally a data table. At the beginning VisuMap will create a random map for the dataset. In this map, each glyph represents a row in the dataset table. But the positions of the glyphs are random. At this stage we can for instance explore the numerical details of selected data points through the context menu. We can also plot the numerical values as diagram. We notice that when we selected data in one window, the other window will automatically highlight the selected data. Now we can create a Pca map for our dataset. To do so, we first open the Pca window that will map our data into the 3D space. We then click on the Capture button to copy the map into the main window. Now we have a 3D Pca map in our main window. In this map, the positions of these glyphs are no longer random. They are ordered to reflect similarities between the data points. We can verify this by selecting a reference data point, then change the glyph size of other points depending on their similarities to the reference point. In this map, the smaller glyphs represent data points with higher similarity to the reference point. We can also visualize the similarity with the help of the value diagram. In order to do so, we first plot all data points in a value diagram, and then use a marker to highlight data points from one region to another region. We can see clearly that how the trend of the curves gradually changes. In order to get better 3D visual effect, let's change the glyph set to a different type. We notice that our dataset contains the average weekly price of about 500 equity stocks in 1 year. That means, each curve in this value diagram shows the price history of a stock. Sometimes we might want to focus our investigation on extremely well or extremely bad performing stocks. We can do that by creating a Pca map of those stocks with the help of the value diagram. We notice that in this map the good stocks are displayed in green color, and bad stocks are in red colors. We can also create Pca maps for a particular time interval. For instance, we might be interested in the behaviors of stocks during a market downturn period. We can do this by first switching the value diagram into attribute mode. And then normalizing the values for the interested time interval. Then, we can create a Pca map for the market downturn time interval. This map shows that green-colored stocks are clearly surrounded by red-colored stocks during this period. This indicates that well-performing equity stocks experienced relatively lower volatility during this period. Now let's take a close look at the Pca service. We notice that the Pca window by default uses the first three principal components to project data into 3D space. These three principal components are displayed by the three drop-down list, together with their eigenvalues. We can easily select other less relevant components for the 3D projection. We can view more details about the principal components through the Pca Analyzer window. In this window, the upper sub-window shows the principal components as bars ordered by their eigenvalues, which is indication for their relevance. From this window we can directly select any component as axis for our 3D projection. The lower sub-window shows the recovery ratio of selected components. The spectrum shows the breakdown of the ratio among the selected components. For instance, the first 13 principal components have together a recovery ratio of about 90%. We can quickly display the data recovered by these 13 components as a diagram, and compare it with diagram of the original dataset. We can also directly display the projection of our dataset onto the selected components. We notice that first few components have larger variations. This indicates that they probably carry more information than other components. The projection to those selected components provides a lower dimensional approximation for the original dataset. We can now save the projection into a new dataset. Then, we can switch to the new dataset through the organizer and show it through the table window. We see that the new dataset has 13 columns. Therefore, it is a lower dimensional approximation for the original high-dimensional dataset.